Today we are going to discuss dipole-dipole forces. First, let's define what dipole-dipole forces are. Dipole-dipole forces are the attractive intermolecular forces between neutral polar molecules. Polar molecules are molecules that have a side of the molecule that is slightly positively charged and a side that is slightly negatively charged, due to the concentration of electrons on each side. The positive end of one molecule is attracted to the negative end of another molecule. These forces are called dipole-dipole forces because a dipole is a measure of the polarity of a bond or molecule. A molecule is said to have a dipole when a distance separates two charges of equal magnitude but opposite charge. These forces are only effective when molecules are close together. In liquids, polar molecules are free to move with respect to one another. Sometimes this movement results in an attractive orientation, an orientation in which the positive end of one molecule and the negative end of another are near each other and cause the molecules to be attracted to each other. At other times, molecules move into a repulsive orientation, in which either the positive ends of two molecules or the negative ends of two molecules are near each other and repulse one another. Even though there is repulsion within a collection of polar molecules, two molecules that are attracting each other spend more time near each other than do two molecules that are repelling one another. Overall, molecules spend more time attracting each other than repulsing each other, resulting in an overall positive net attraction in a group of polar molecules, explaining how polar molecules stay together even though there is some repulsion. For molecules of approximately equal mass and size, the strengths of intermolecular attractions increase with increasing polarity. For example, propane, CH3CH2CH3, has a molecular weight of 44 AMU, and acetonitrile, CH3CN, has a molecular weight of 41 AMU. Acetonitrile has a greater dipole moment, meaning it is more polar than propane, so it has greater dipole-dipole forces and has a higher boiling point. For molecules of comparable polarity, those with smaller molecular volume experience greater dipole-dipole attraction. This is because molecules must be able to get close together in the correct orientation for dipole-dipole forces to operate. It is easier for small molecules to get close together than it is for large molecules. A special case of dipole-dipole interactions is known as hydrogen bonding. Hydrogen bonding is an intermolecular attraction between the hydrogen atom in a polar bond, particularly HF, HO, or HN bonds, and the non-bonding electronegative atom, the FN or O, in another molecule. For example, a hydrogen bond exists between the hydrogen atom in an HF molecule and the F atom in an adjacent HF molecule. Hydrogen bonding is considered a unique dipole-dipole attraction because Fn and O are so electronegative that a bond between hydrogen and any of these elements is quite polar, with hydrogen at the positive end. Since the hydrogen atom only has one electron to bond with and no inner electrons, the positive side of the bond dipole has the concentrated charge of the partially exposed hydrogen nucleus. This positive charge is attracted to the negative charge of an electronegative atom in a nearby molecule. Because hydrogen has so few electrons, it is small and can approach an electronegative atom very closely and thus interact with it. For example, we can see how molecules of H2O and NH3 demonstrate hydrogen bonding. The lone pairs on the O and N attract the positive H atom,